Transport at high temperatures, things like something that Marco was talking about. Lately, I've been, well, not lately. I started a project related to monitor. So I'll set that we'll talk about that. But ties into symmetry, so specifically like non-abelian ones. Yeah, the first poster section. Yeah, I will have to. No, yeah. But and this yeah, the poster isn't about.
Go for it. Yeah, I'm ready. Thanks. So we left off last time with the general Nilaflam quantum error correction conditions or quantum error correction criteria. I guess it's probably worthwhile, since there were a few questions, to kind of discuss this a little bit more. These hold true for general errors. So the errors E that we've looked at so far have been Pauli. They've been unitary, they've been Hermitian, and they've been obviously diagonalizable because of the first two. But in general, none of those criteria have to hold. In Liang's case, this was a loss operator, which is not unitary, it's not Hermitian, it's not even diagonalizable. Okay, these were still holding. Now, there was a question that was important that was asked. Well, if you're having general errors here, in what sense is one error undoing the effect of the other? That type of intuition holds 100% in the case of Pauli's, because you have errors that are Pauli strings that you undo via applying the same error again, because the thing squared is equal to identity, right? So anytime you have a Pauli string and you diagnose a syndrome corresponding to the error space that Pauli string took you to, in order to recover, you apply that error again as a unitary operation, and that will undo the effect of the error. And what these conditions are saying is that if you have two errors taking you to the same error space, then they better be able to undo the effect of the error inside the space. Meaning that their product, another way to say this is that their product is identity on the code space. So now, when these are not Pauli strings, can we still think of one error undoing the other? I think so, but not as rigorously, but the intuition still holds, because this is literally saying that, but only within the code space. So let's say this is not some diagonalizable thing, some monstrosity, but what these conditions are saying is that if we have two errors that take us to the same error space, then within the code space, they better be undoing each other, in the sense that together they implement nothing but the identity operation. Okay, so these errors don't have to be unitary, and really this one, if it's not unitary, you can't really apply it as a unitary map to actually undo this effect. But what this condition is saying is that the product of the two within the code space is equivalent to not doing anything in the code space up to some rescaling. Okay, so in the case of Pauli's, you literally undo it by applying E-dagger. In the case of other operations, you're not going to just apply E-dagger. It might be some thing that takes into account this reweighing by this coefficient. It's going to be part of some channel. It's going to be nasty. You know, if I have some time, I can go over some recovery maps that are like the PETS map. And who's heard of the PETS map? Yeah, okay, so yeah, so it might be useful to cover that, but not right now. So in general, the recovery is not just going to be this thing, but in the Pauli case, it literally can be that. Okay, so this thing is non-zero when the two errors take you to the same error space, because then the effect of the product of the two with this dagger takes us back to the code space. So there's going to be something in there. But if these two errors take us to different error spaces, then the dagger of this one just takes us, first you take this one, you apply to the code space, you get into one error space. You apply that one backwards. Well, you don't make it back to the code space, because without the dagger, this thing would have taken the code space to a different error space. So then here you're in some other second error space, which is not the code space, so it's 0. Okay, so when these things take you to different error spaces, this thing is 0, you're done. When these errors take you to the same error space, then you have to worry about whether they can undo each other up to within the code space. Okay. Any questions about that? Yeah. Well, there's nothing to undo there. There it's, let's say your error takes you out of your code space. Can you detect it? Yes. That's 0 when that happens. Now you say your error can't take you out of the code space. Oh no, what happens? Well, now we have to ask the next question. What did it do within the code space? Did it do something non-trivial? Then we can't detect it. Then it's an actual error that we can't detect. Did it do something trivial? This is a non-zero coefficient then. It did some identity map. Okay. And we saw that. Okay, so I alluded to this idea that you can treat noise models and errors, the action of errors, as an attempt by a malicious environment to probe your logical information. Okay. Now, this environment there's something here that you can actually make quantitative. Okay, so these statements can be made quantitative by looking at something called the complementary channel. So if we have our system and we have some noise in there we can't control, then when we send our information through the system, let's say it's already encoded, so this is already a logical state. We have a noise channel, and we know what this channel looks like. It's in Krauss form. Who's heard of Krauss form? Do I need to go over Krauss form? I think we're good. So for those of you who don't maybe know this, this is just the general form of a process that maps density matrices to density matrices. Okay. In general, processes are non-unitary, and when they're non-unitary, they're going to be linear combinations of the same things acting from one side and the other. These things have no restrictions on them other than that this thing maps density matrices to density matrices, namely that it's trace preserving, and that actually means you have to satisfy this. These things have to add up to the identity matrix. So that's it, and this is the most general process. I'm not going to derive it, but just take my word for it. So where did this come from? Well, this came from, this can be made to come from taking a larger system, applying a unitary, and tracing out the system that you've enlarged, just tracing out the subsystem to which you've enlarged this system to. Okay, this is called Stein-Spring dilation formally, but you can just think of taking a larger system volume of the unitary and tracing out half. Okay, and that half we're going to call the environment. Okay, this can be done several different ways. Here, I'm actually even dropping the larger system state because I'm cooking up this type of weird lopsided looking operator. That's like this. But this is just shorthand really for taking, instead of rho L, taking rho L to go to rho L times environment. And then, sorry, J having this map to from 0 to J. There. So then now we're good. So if we start with this thing, we evolve under this unitary, which there's going to be other pieces that touch the non-zero environmental state that we can just ignore. And we evolve under this unitary, and then we trace out this second factor. You're going to get that channel. Okay. Was that, maybe it's, I don't know, who's seen this type of derivation before? Okay, great. So yeah, I was hoping you would say that. So, okay, that's fine. But what if we do that? Did you see this last week? Now, if we trace out the system, what happens then? This is underappreciated. Okay, I got 3 papers out of this. As a postdoc, and Liang and I got like at least 2. What? The system is the first factor. If we trace that out, what do we get? And we get another map called the complementary channel, which takes our system, okay, this is still acting on the system, but now it spits out what the environment sees. What is this environment? It's this environment we made up that's commensurate with this noise model. Okay. And it also has a very nice, elegant Krauss form. Not Krauss form, sorry. It has a form, analytic closed form. Yeah. They're indexing over the Krauss operators. So, oh, right, good. So, you know from this Stein-Spring dilation stuff that you need an extra state of the environment for each Krauss operator that you get, right? That's what happened when you initialized your environment. You had to make it so that the number of states in the environment is the Krauss operator. These are literally those states, okay? So the environment is receiving a density matrix whose matrix elements are literally expectation values of products of the noise operators. And that should make you think about something as it related to the null-Flam conditions. Yeah. Well, so I can transform this set of Krauss operators into, by rotating them by a unitary little u, and combining them in this fashion. Yeah. Okay. Good. So we got these new Krauss operators here. Let's call them n prime, j. And is this channel left invariant under this transformation? It's the same channel, in other words, right? This one, well, let's look at it. I think if we stare at it, it should also be invariant, right? Is that right? I think it just applies a unitary transformation u to the to the basis. Well, there's also this idea that there's a minimal number of these, and you can have channels with larger numbers of Krauss operators. It's not the minimal number. In that case, you're going to have a larger density matrix here. So that then changes the size of this thing. But the amount of information it's extracting, I do not think it changes. Because it's still going to extract the same type of expectation values. Now, I don't have a proof for that part. Yeah. No, I think that's all the ambiguity. If you restrict if you write your Krauss map in the way that this is the minimal number of Krauss operators, I think this is it. Well, unique up to unitaries on the density matrices that change these. Yeah, I would wager, I would bet you $10 that it's unique, but I don't remember the rigorous proofs or anything of when it's important. Okay, I hope it convinced you it's important. Like mathematically, you know, there could be some minor caveats, but I'm going to assure you that they're minor. This is still extracting information. Yeah. Yeah. I was confused by your joke.
No, what's the asymmetry between environments?
Asymmetry.
Asymmetry. Normally, you get some reduced density matrix. Well, sorry, so you start out with the system, direct product with the environment. Then you unitary evolve it, and then you trace out one or the other.
Right.
So you normally trace out the environment, then you get the left side, cross out with that. Systems that's
Right.
to the opposite. Seems like there's a symmetry. What's the asymmetry in what you call environment?
The initial state. The initial state. The initial state is that's one of the asymmetries, yeah. All the information is in the first factor. Okay. This is kind of an appendage. Well, it's ancillaries we can't control. Right. Right. That's why we got to trace over them, because we can't control them. There's nothing we can do, on there that allows us to do more general maps than just tracing out. We just have to forget about them.
How is it if you traced over the
Yeah, so this should be an arrow pointing down. So that we start, these are both maps on the system, and they map you into whatever the output of the noise channel is, which is still the system usually. And then this one maps you to the output of what the environment. Yep. Yeah. Here. Yeah, like if we're saying the only ambiguity is, well, no, but if you have a different number of Krauss operators, you're going to have a different number of states, so the spectrum will have more eigenvalues. Oh, you mean on this level? Same, these two should have the same spectrum? If rho is pure, then it's factorizable, then, but even then the eigenvalues are multiplied. Yeah, but if it's mixed, it's kind of, yeah. Oh, but I mean, like, being facetious aside, this offers a really nice way to peek into what really the environment gets, but really the properties of the code and the and errors from the perspective of this environment that we've created that's associated with this noise channel. Okay, and there's many different things you can gain from this side it's easier to extract than from that side. Okay, so bounds and trade-offs on code parameters and stuff you can extract from this side more directly. Okay. For example, you should be able to see something here. Namely, remember these they're not mine, they're Nils and Laflamme's error correction conditions, right? So the environment is extracting these expectation values. And if we have a noise set that satisfies these conditions, then we can plug them in here, right? This is an encoded state. So this is equivalent to, we can stick in a little pi here. We can stick one here. We can move it all the way over here. And then we have pi n and pi, right? And if we now plug in pi n and pi and say they're equal to a constant, what does this give us? this gives us a matrix of constants, CJK, times trace of the density matrix, which is just otherwise known as 1. So in the case that your errors are correctable, the environment gets absolutely nothing from the code. It only gets information about the noise. Well, we don't care about that. Okay. And this I believe is an if and only if. Okay. And if you have situations where the environment will get some information out, this state will contain that information, and looking at the trace distance or some other norm, some other distance or fidelity of that state with respect to the state that you would have had if you corrected those errors exactly will help you quantify how well your code is doing against the noise channel, okay? And also, this sometimes helps you that this space, the dimension of this space is just the number of Krauss operators, the minimal number of Krauss operators, and the dimension of this space can be huge. So in some cases, you win by studying something that's fewer dimensions. Okay. So, right, so we've taken a look at Pauli channels, and Liang has introduced us to non-Pauli channels. And we're going to do the qubit version of the channel that Liang introduced, which is non-Pauli, because it's important for experiments, and it's in order to show you that not everything in error correction is this digital Pauli-based error correction. We do that because it's simple. We do that because we can analytically derive things about it. But in real experiments, you don't have Pauli channels. Okay, you have crazy channels. Okay, so a simple example of a non-Pauli channel is precisely the restricted version of a channel that Liang introduced, is amplitude damping. And one of the highlighting features of this, I'm going to write 2 Krauss operators for the noise. It's first, then you tend the product. One is this, and the other one is this. So one feature that can happen for a non-Pauli channel is that there's no identity Krauss operator. There's just this guy. This is identity up to leading order in P, but we're talking for all P's. This has to be a well-defined Krauss map. And this is precisely the back action Liang was talking about, that you're never going to have identity applied. You're never going to have no error. And so even when you don't have some sort of a concrete stochastic relaxation process like this jumping from 1 to 0, you're still going to have to take care of some sort of error. So if you take the amplitude damping channel that Liang introduced and you truncate the Fock space to the first 2 Fock states, you get this. Okay, so they're the same channel when you restrict your oscillators to the first 2 Fock states. Okay, this is A. It's the first little sliver of A. Yeah.
Always decompose the 2x2 matrix using I, X, Y, and Z. Why do we want to study this now function?
Because we can decompose each of these Krauss operators into X, Y, and Z, our error correction will work. But we still need to quantify how well we can protect against the channel itself. Okay, and not the little matrix basis constituents that each Krauss operator will have. So let me show you, let me do this calculation, and hopefully you can ask this question again if it doesn't make sense. So right, so for this example, you might be asking yourself, well, we're going to do this with 4 qubits, by the way. We already know the 4 qubit code can detect arbitrary single qubit error, so what do we care what channel looks like? If the channel is only acting on one of the qubits, we don't care. Well, so the problem with this channel is that it has no identity Krauss operator. So every single Krauss operator of the combined channel is gonna have weight 4 Krauss operators. Things like this, and then things like this, which are characterizing single jumps, and then there's 2 jumps and higher. This I call a jump, because it's a relaxation event. So we can't readily apply, we can't readily apply the framework that I showed you before with where we had single weight errors detectable to this channel because we don't have single weight errors. Okay, but the beauty of the 4-qubit code is that it can actually not only detect but correct this channel to order p squared. Okay, so here now we have to plug in these Krauss operators and look at the error correction conditions to see how well this code will do. And it won't protect exactly against any of these, but it turns out it can do so approximately well. And we're about to calculate that. So we have these Krauss operators, and you know, this one applied from the left and the right is order p, right? The ones with 2 1s and higher are sort of order p squared. So we kind of just focus on looking at these and plugging them into the null-Flam conditions. So first, plug them into the null-Flam conditions. So first, yeah. So, all right, let's so here's, let's just do it. So here's one error. So if we so what happens if we apply this no jump error followed by a jump error? Well, remember our 4-qubit code, which I don't list here. Sorry about that. Right? So if we apply 2 errors and there's only one 1 here and there's no 1 here, well, this is going to change the Hamming weight of these states. It's going to change it from even to odd because it drops one of the 1s and maps it to a 0, right? Or it annihilates the states completely. So then we don't have to worry about it at all if it acts on the 0 state. So if there's this asymmetry, then we know this is going to be 0, just because the error space that this gets you to is just orthogonal in terms of the support of the states. Same with the 1 state. Now, then we have to worry about this type of situation. Oh, and same with the off-diagonal case. Well, so this type of situation, we can just calculate by hand. So if we apply this, this thing, there it is, to this state, this is going to get killed, and this dropped. That dropped this 1 down, and it gave you a p from the square root of 2 here, and then, sorry, it gave you a square root of 2 here from that square root, and then it gave you a p from that. And then there's like probably a few 1 over minus p's, I don't care. And then this one just gives you the same thing. And this is otherwise known as p over 2. We do the same thing here. This is just the norm of this state. So now this will act on these two. In this case, it drops this to a 0 and then annihilates that. So we're left with just this state with that being a 0. It's the same thing here. So is this portion of the Nilaflam condition satisfied? Yeah. These are called, by the way, the diagonal pieces of this when you have the same code state on either side and the equality between them are called the non-deformation condition. Because you can think of an asymmetry in the expectation values as a deformation. And the ones where you have a different state here than here are called the orthogonality conditions, subconditions. And so together, the non-deformation and the orthogonality conditions give you the Nilaflam error correction conditions. Okay, great. So that's taken care of some pieces, but now we also have to take care of the product of this back action type no jump operator and project that into the code space. Right? There's no non-identity Krauss, so we can't, we have to deal with this thing. Well, so if we act with on the logical zero, okay, so here's logical zero. So we get nothing here. And then we get 4 square root of 1 minus p, because there's a 1 here for each of them. So that's just 1 minus p squared. Okay. And now we act with 4 of those on the logical 1. Well, we just get a 1 minus p because there's only 2 copies of 1 in the state in each one. It's symmetric, so it doesn't matter. And then you just have the state back. Okay. Okay, so now we take this and plug it into here. Now, why is there no, so I'm arguing that we only need to worry about the diagonal conditions, the deformation conditions when there's a 0 here and a 1 here, because these don't cause transitions from 0 to 1. Why do they not cause transitions from 0 to 1? Because the operator here is diagonal in the basis, and we have different Hamming weights for the code, the basis states participating in the code words. So there's just no way they're going to map and change the Hamming weight and connect the 2 code words. So we only have to worry about the diagonal ones. So if we do the diagonal piece, well, here is where we Taylor expand. And here's where the square root of 2's are, did I do it right? So we should Taylor expand, and there should be a 2 somewhere that we cancel, because the answer is, if I did that right, this plus order p squared. So let's stare at this and see where I made a typo or something. Right. So Taylor expanding this gives you 1 minus 2p plus whatever. And there's a 2 here. And that 2 has to be compensated by a 2 here. Where'd that 2 come from? Well, there's 2 different states here. So when we take this thing and calculate its norm, which is just the same thing as calculating the 1 case, then these are going to crash into each other twice, and we get a 2 here. Okay. And so this 2 is here, and we get satisfaction of these criteria to leading order in P. So even though this thing is weight 4, in terms of Pauli's, it sounds really horrible. It's actually not as bad as you might think. Not only can we detect it, we can also correct it to that order. Remember, these are products I'm taking, so I'm actually correcting single amplitude damping, meaning I can correct the error set that consists of 5 errors, this error, and the 4 different ways to lose 1 particle in each of the 4 qubits. It's a set of 5 Krauss operators, and I can actually correct them up to order p squared. Yeah.
fractional condition violated order PS squared, the recovery channel, they like it gets the incorrect up to PS squared. Maybe it uses some EM.
Yeah, it's not, I wouldn't say it's trivial. You have to go through the actual fidelity calculation, which this was done in 96 or 97 by Ike Chuang and collaborators, Yamamoto, I think. They do go through the fidelity calculation. It is true, and in some sense, you could maybe make it sound trivial by saying, well, you just apply whatever, like you Taylor expand these in the beginning, and then you apply the theorem for the error correction conditions, and then you're not going to get any other thing. But you can't quite do that, because then if you Taylor expand them in the beginning, they're not a cross map, right? Like Liang did when he expanded actual photon loss as 1 plus A. That's not a cross operator. Cross operators have to be trace class. Their trace norm has to be finite. And A, the trace norm of A is not finite. A just blows up. It's an unbounded operator. It's horrible. But in the real world, you don't have unbounded operators. You have these nice, well-behaved cross operators for this photon loss channel. Same kind of thing happening here. Yeah. It's not obvious at all. You add some arbitrary unitary, it's going to screw everything up.
Like, for example, if I have amplitude damping and some Pauli error, I can construct a channel which will be, I think we can construct a channel which will control all these cross operators. And then the Neal-Laflamme condition. So you're saying it would still be only violated up to linear.
You would have to check, because I wouldn't, don't pin me on that. You'd have to talk to my lawyer about that, because I don't think it's always going to work. But because you got this weight 4 guy, you have to see how that talks to whatever weight 1 guy you've introduced. It could be non-trivial. It could maybe work. I would say you just have to check.
Then I'm not, until I do that, I'm not guaranteed that any single qubit error even approximately can.
Well, it's a different error set. Every time you want to check, you have, with a given error set, you got to run through the Neal-Laflamme conditions just to check that error set. Okay, if you expand the error set, maybe it won't work. Like for bosonic loss, somebody asked about gain. Well, if you have A and A dagger, well, it doesn't work if you have 0, 2, 4 binomial code, because your error space is only like 1 and 3. It's only one error space. If you got gain, you go back into the same error space. You got 2 errors mapping to the same error space. You're not going to correct them. So you might run out of error spaces to coincide with the errors. I'm not sure. It's a homework exercise. Solve this person's problem. Yes. Yeah, I blurted it out during your lecture. Thank you for your question, Liam. It's a good question. So yeah, we actually had a student, Lin Shu, try to come up with a map. And when I do this map, I always have a bunch of questions about it. So I didn't include it off the bat, but I think it's important now that you lectured about these. So you can map to the kitten code by just adding up adding up the little things here and mapping them into Fock space. So you add up all the things here and you map to Fock space that's the sum of the 4. And then you add up to these and you map to the Fock space 4. Here you map to the same Fock space state, which is 2. So the Hamming weight spacing in this binary space winds up being equivalent to the actual integer spacing in Fock space. And the error spaces are also kind of the same. This one drops your Hamming weight by 1. It takes you to the weight 3 or the weight 1 space, depending on which one of these you're in. This one will go to the weight 3, this one go to weight 1. Well, but if you have 1 photon loss, this one goes to 3, literal 3, this one goes to literal 1. So the distance here is kind of the same idea. Yes. Good. Yes, this. it's often argued that the bosonic setting is simpler from a combinatorial perspective, precisely because of this type of situation. When here you actually have lots of error spaces, and here you only have one. But here, all the three different error spaces are really kind of the same as this one error space. They're just for the fact that there's combinatorial, like 4 different ways you can lose a single photon. Sorry, 4 different ways. There's 4 error spaces here that are sort of corresponding to a single. What is a single error space here? Yeah, right. I would say, yes, that's true. You don't have a combinatorial blowup, but you also don't have thresholds in a single bosonic mode either. So, you know, it's a bug and a feature. You have to live with a combinatorial blowup and the different possibilities of having errors in a multi-qubit setting if you want to have arbitrarily good error correction, if you want to have phases of matter, if you want to have a thermodynamic limit. It's just something you're going to have to live with. If you're okay with just implementing an increased gain in the logical rate, then you do save on resources, and you are more what people call hardware efficient when you encode in a single cavity or a single mode. You can get the benefits of basically the 4-qubit error detecting code in one mode. Now think about that. That's pretty cool. Okay. Because here you're using 16 states, right? 2 to the 4th. And here you're using 0, 1, 2, 3, 4, 5-dimensional subspace of your infinite dimensional Hilbert space. Here you have 4 little whatever devices you have, each of them 2 levels that you're using. Here you have 1 device. You're just going deeper into the Hilbert space. And the error correction capabilities are more or less this. Error detection capabilities here are more or less the same. You can correct 1 loss here, and you can correct 1 loss here. Right? Yeah. Right. 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 Well, then this thing is just too trivial for you. That's already non-trivial. The fact that you shouldn't think it was trivial to show all that. Yeah, you're saying there's some maybe continuity or analyticity around the p=0 case that you can use to argue that there should be some sort of expansion. Well, Ali and I don't think so. Off the bat, it shouldn't be trivial. Maybe, I mean, yeah, basically that's what we did. We showed that it is indeed true. Why should it be not trivial? Because before, all we showed was that this thing can detect weight 1 errors. This thing is weight 4. Okay, the code can detect weight 1. This is weight 4. It not only detects but corrects up to some error, up to this thing. You can, this type of thing should kind of scale up. Yeah, this is the simplest example of this type of behavior. Yeah. I guess in the end, you're going to have some fidelity, some approximate equals to rho thing. And it's going to be for Pauli channels, and for these channels, it's going to be like to leading order for this code equal plus some order p² corrections. The question is, where do the p² corrections come from? For the Pauli channel code, the leading order Krauss operators are corrected exactly, or detected, sorry, exactly. And then the higher order guys are not at all detected or corrected in general. For this type of situation, all the Krauss operators are not detectable, but each one is detectable to some order. So in the first situation, you had sort of, you've taken out some small set of like dominant Krauss operators and left the remaining ones. But in this case, all of your Krauss operators kind of like the same order, and then you just partially correct every one, partially detect every one in this case, but in general correct. And these types of maps are very important, not only because they're more hardware efficient, but also because this is what you really see in experiment. You do not have identity Krauss operator in experiment. So you don't have this luxury of like saying there's no error on some qubit. You're always going to have some error on every single qubit in general. And this type of framework shows that error correction and detection, at least the detection here, is possible even for those situations to the same degree and the same level of infidelity that you would for the exact Pauli channel case. Yeah. Okay, so now I'm gonna the thing here mapped this 4-qubit code into the binomial code, but there are other mappings and embeddings of the 4-qubit code as special cases, very simple cases of more general code families, which are important. One is tying it back to the original first error correcting code, the short code. Let's rewrite our 4-qubit code, which I've put over here. Let's rewrite it in plus minus basis. So take the superposition plus minus of these and do that. And then if you stare at it, you'll see that it is a just tensor product of 2 Bell states, 2 plus Bell states and 2 minus Bell states. Okay. Okay, well, this gives us a little bit of a pattern. So let's see. So what's happening in this other basis? This other basis, by the way, is just good enough of a basis as the first basis that I used because it still determines the same subspace. You can use other multiple bases to determine the same subspace. So what's the pattern? Now, well, you notice your Bell states have 2 qubits each in them, and there's 2 copies of them. And in this sense, you can construct this type of basis by using concatenation, which is doing a recursive construction of encoding on top of encoding. And we can do it as follows. So first we start with kind of like a stupid repetition code. It's not majority vote because there's no majority. Okay. And but let's just do it. Let's just encode each bit into 2 copies. Then we do a change of basis on that level. And then we duplicate that first step again, but with this basis now. So this is a repetition code against bit flips. This is a repetition code against phase flips. And so we're taking care, by concatenating the two, we're taking care of both bit and phase flip, some degree of bit and phase flip protection. And that gives us this code. And in fact, that gets us a code that can detect both bit and phase. But now we can change knobs. So now instead of having 2 qubits per copy and 2 copies, we can do 3 qubits and 3 copies. Now, this is the original quantum error correcting code. It's the short code. It is large enough to not only detect, but correct single qubit errors. Correction will work the same way as I showed. The reason I didn't show it with this code is because too many error spaces. There's a combinatorial blow up in the different number of errors that can happen. So there's lots of things to keep track of. So I just decided pedagogically it's easier to handle with 2. But 2 is too small to correct. But this resolves all the errors in some way that you can detect and correct. There's still degeneracy. Even here, you have multiple errors taking you to the same error space. But the error space structure and the size of this embedded Hilbert space is big enough so that you can actually correct all single qubit errors. Yeah.
You don't need to then, you don't then use the plus minus basis, you know, double it.
We already did that here by doing it, the 3. So first, this step is here, and then this is there. And for general knobs, you obtain these generalized Shor or quantum parity codes. Okay, the 4-qubit code can be thought of as a stabilizer code. Now here we go. So there's going to be a whole lecture on this lecture, however much I can get done. So what is a stabilizer code? Well, let's recall this observation that we had where, I'm sorry, I'm rewriting it not in the square way. So I mentioned last lecture that there's certain operators that don't take you out of the code space, but they're also detectable errors because they don't do anything in the code space. So namely, there's this one. If you apply ZZII, then you get a +1 out. So namely, the code words in the entire code space is in fact the +1 eigenspace, this eigen subspace of this operator ZZII. There are other operators that do this. IIZZ satisfies this. By symmetry, you can see the same thing. ZZ in the second column. And all X, I think I've mentioned already. Also, those ones just permute the two basis states in each code word, but don't do anything else. Don't permute the code words, don't do any logical anything. So what else is interesting about those three operators? Well, they commute with each other. Okay. And they, because it's Pauli's, they form a group. That's fine. So what's a group? There's inverse, there's identity, and group multiplication. Multiplying two things gives you the same thing in the group. A nice way to write a group, which is this set of all products of powers. Yeah, products of powers, is using its generators, namely what are the things you put in here such that all the products of powers of these things are the group. And the generators here are these three things. Right? If these are +1 eigenstates of this thing, they're +1 eigenstates of XXYY or YYXX or ZZZZ. All the products also work out because +1 times +1 is also known as +1. Okay, what else do we get? There's a lot of structure here, it turns out, and this type of code is called a stabilizer code. So this group is special. What is a stabilizer group? Well, this group admits the code as the joint +1 eigenspace of all the generators. So namely, this has half the states in the space is +1 eigenstates, half is -1. This partitions it in a different way. This partitions the space in a different way. But together, if you take the intersection of all the +1 eigenspaces, you get the code. It might be difficult in general. I think you just got to crank. Yeah, you're gonna have to count, but it might be difficult in a many body setting. But yeah. So stabilizer codes have notation. So they're used by double brackets because they're kind of the analogs of classical linear codes, which are used for which you use single brackets. NKD here is N is the number of physical qubits. K is the number of logical qubits. So for our code, we had a 4 here, a 1 here, and then this is called the distance. D-1 is the number of qubits that a detectable error can act on at most. Okay, it's the number of qubits that can have errors on them and the code can still detect them. So for us, the distance is 2 because 2 minus 1 is 1, which is the number of qubits that our code can, number of qubit errors that our code can detect. Okay. So what are the advantages? Well, there was a few questions about, given a code, which is just some abstract subspace, what are the parity, what are the check operators? What are the syndromes that I use to diagnose my errors? Code is fine, and maybe in principle, nil flam will tell you that a code can detect or correct certain things, but how do I actually do it when I have to do this medical syndrome extraction circuit, right? What do I measure? Well, in general, that's a hard problem, but for stabilizer codes, you get it for free. And what are the syndromes, the check operators? What are the check operators for stabilizer code? The stabilizer generators themselves. Remember, what did we want for a check operator? We wanted a check operator to tell us where we are. We don't want a check operator to move us from some airspace to another airspace. We want a check operator to help resolve, you know, it needs to be some good enough set of quantum numbers so we don't resolve within each space, but we figure out which space we're in. Well, what do these do? If they're in the code space, they're all +1. If we're in some airspace, then one of them flips, maybe another one flips. And this binary string helps us nail down the airspace. Okay. So so once we have a stabilizer group, we get the set of syndromes for free. Once we have a stabilizer group, we also know what the code space is. We don't have to write cat plus cat plus cat plus cat. This gets really unwieldy if you ever tried it for the 9-qubit surface code. Right? But for the 9-qubit surface code, now that I know all of you supposed to know what that is, you can just write down some crosses and some squares and you're done. You know what the ground state will be. And this is a very general idea that has been extended ad nauseum to other spaces. And Leon will talk about lattice codes, quantum lattice codes, or otherwise known as Gottesman-Kitaev-Preskill codes, where the stabilizer framework is done using not Pauli operators, but linear displacements in the phase space of this XP or IQ oscillator space. So any type of commuting set of unitary operators that have +1 eigenstates can be thought of as a generalized version of this. Instead of using Paulis, you use displacements. Okay. There's a special class of stabilizer codes called CSS codes. So in the stabilizer group, you had a set of generators. This is not a unique set, but for CSS codes, there exists a set such that each element of the set of generators is only Z or only X. This is the case for the 4-qubit code. And if you had like X, Y, Z, Z, whatever, then you don't have all Z or all X, and that's not a CSS code. And when you do that, you gain even more structure. And now you start making connections to classical coding theory. Remember, we thought of this 4-qubit code as a concatenation of a bit and a phase flip code, sort of two classical codes embedded in quantum in two different ways. Well, general CSS codes can also be thought of that. So because you have all X and all Z generators, you can map all the Z generators in a matrix whose row just tells you whether there's a Z there or not. You can do the same for the X generators. Not a very big matrix there because there's only one. Okay, and then you get two matrices. These turn out to be what's called parity check matrices of classical codes. So your sort of codes, the repetition code is one of those types of matrices. The repetition code parity check matrix. So for the repetition code, remember we had ZZII, IZZ, and the parity check matrix is like that. It's like this nice diagonals of ones for larger codes. Okay, great. So you can map to these matrices. And these matrices, because they correspond to stabilizers that commute, the commutation condition can be mapped onto these matrices, and it's just that 1 times the transpose of the other is equal to 0 modulo 2. Okay. So then we just need a couple matrices that satisfy that, and then we're done. We have stabilizer code, right? Once we crank out this machinery, get all the Paulis, and we're done. Well, where do we get our matrices from? Well, there's lots of matrices in classical coding theory. We just picked 2 classical codes whose parity check matrices satisfy this condition. And there's a nice, well-defined condition for the classical codes to have such that this is satisfied. And we take any 2 classical codes that satisfy that, and we get a stabilizer code out that's of CSS type. This is called a CSS code. And it goes down, starts going down this path of taking classical codes, 2 classical codes that interact with each other in some way that can be translated into a commutation condition on the stabilizers, and you get a code out. There's several different code constructions like that. I can show them to you. Not all of them have been nearly as well developed as the CSS one, and I think there's more to do there. So we can talk if you're interested in research. Yeah. Yeah, I think you can do this with any 2. You can do X and Y, you can do Y and Z. No, you're gonna have 2 out of the 3. Yeah, because it's CSS, so you only use 2. And the convention is that it's X and Z, because of this symplectic mapping where Y is like 2 ones. You know what I'm talking? 1 0 0 1. Correct. Okay, great. So we made a connection to classical coding theory, which classical coding theorists noticed in like 90 whatever 7. Right. And then the next thing is this thing Kitaev noticed is that these matrices also make contact with homology. So now I'm getting out of my comfort zone a little. So if you start asking questions about this, I'm going to refer them to Alex, but please do still ask questions. How does this work? So, well, in the homology side, there's this you basically have manifolds and things you can tessellate and triangulate. And on this triangulation, you can define boundary maps, which kind of add up your elements of your triangulation in some way that you lose a dimension every time you apply the boundary map. So the boundary of a triangle filled in is like just the 3 lines, okay? And you can keep doing this and drop a dimension every time. You can define boundary maps that kill a dimension every time. And when you do that, you form something called a chain complex. And the defining condition that these boundary maps have to satisfy is that boundaries don't have boundaries. So these boundary maps are defined in such a way that, you know, taking you 1 dimension down and then doing it again in the same object will kill it. Well, it turns out we can associate a CSS code with a chain complex. If we take this space to be the space of X parity checks, this space to be the physical qubit space, and this is a 4-dimensional binary space for 4 qubits, and then this space to be the Z-check space, then we can take our 2 matrices and use them as boundary maps that map you between the 3 spaces. And our commutation relation for these is exactly the boundaries don't have boundaries condition of the chain complex. So this beautiful correspondence was noticed early on, and it led in part to this breakthrough in asymptotically good QLDPC codes, which is just a whole bunch of classical coding theory with the CSS stuff mapped on top of it to make a quantum code. So the fact that we can connect this, we can easily make quantum code constructions out of exotic tessellations of exotic manifolds and classical codes allows you to plug into this very, very well-developed, 2 very well-developed field of homology / topology and classical coding theory. Yeah. Yeah, so this tells you which qubit participates in which check. So this is some binary space that is of the checks. Each one is a check, and then this map tells you which qubits participate in it. So that's why the map is basically the actual check matrix, which literally is a 1 whenever you have some qubit participating in that parity check. Yeah. Yes, it does. It does. Yes. Alex will talk about it. I'm going to defer. Yeah, so there's properties of these chain complexes, like whether you have non-contractible loops and stuff in them, and those translate to the distance and gate properties of the code. Yeah, there's a whole table that is in one of these papers that I didn't include here, but you can infer a lot of things about properties of the code by just the underlying chain complex or the underlying classical code. Well, here dimensions the number of qubits. And if you take kind of the opposite arrow, then I think it's cohomology. This is a very loose analogy with my pictures of triangles, but yeah, I think so. I think this is one triangle, and then you get to 3 lines. You can flip these maps, and then I think you get cohomology and dual relations as well. Well, I would say the spatial dimension of the chain complex does matter when it comes to the properties of the code. Okay, you don't see that through this mapping, but it will matter. Okay, and I think Alex will talk about this eventually in his lectures. So I'm out of my comfort zone. I don't use this on a day-to-day basis, but yeah. You apply the boundary map 3 times? Oh, length 3 chain complex. Yeah, a quantum code only requires 3 things and 2 maps between them. Well, to define, you only need 2 boundary maps to define a quantum code, and you need 1 boundary map to define a classical code. I'm mapping the choice of what you pick for X and Z stabilizer generators to boundary maps in homology, yes. Yes, you can embed it into a larger chain complexes with other pieces in it, yes. Yeah. Okay, and last but definitely not least, let's arrange the 4 qubits into a square. This is what I already did. And we can have this nice tic-tac drawing where we shade in with white any stabilizer that's of X type in corresponding to a square whose vertices are the qubits that this generator is supported on. And then we shade in gray any Z-type generator that'll be an arc or a square. It'll be an arc or a square here as well, whose corners are the 2 qubits that this Z-type generator is supported on. So our 4-qubit code looks like this. And then let's just get nuts. Right? We can extend this construction in this way. So here, please ignore the black qubits. These are demonstrating the ancilla that you would use to measure that particular check operator in the same way I told you how to measure the ZZI repetition code. So, but those are just ancilla qubits. The data qubits are these white. So what I had red here are these white circles. And you can scale this type of construction up and you get these nice checkerboard patterns. And this is called the rotated surface code. This is what Google is trying to build. Okay. So the 4-qubit code is a planar rotated surface code made out of 4 qubits. And you can do you can close the boundaries on this thing, and then you get the torque code. You can poke holes in geometries that are large enough, and you get logical qubits that way. You can go to 3D. You can do hyperbolic manifolds. So this is where some of the chain complex stuff starts to come in. You can do fractal geometries. Some of you are on these papers. Who's on one of these papers? Maybe not. Okay. So this is a whole cottage, this is a whole industry. Okay, literally industry, like companies. Yeah. Well, you go backwards. You start with a chain complex, you map to a CSS code, you get your stabilizers, you get your code space. Me? Personally or in general? In general, yes. Yeah. Yes, the features of the chain complex will tell you how good of a code you can construct. Which means, yes, you do know a priori, once you pick a chain complex, you can use the features of the chain complex to figure out some details about the code. That's what Alex will talk about. Just getting you excited for his lectures. Okay, so by popular demand, I wanted to also make connection with topological codes a little bit more by sort of putting side by side all the new jargon that I hope some of you learned today, some of which I hope you learned today, and the jargon that you may or may not, you may be more familiar with that comes from the surface code. So this is kind of a fresh table, so there might be errors, but let's go through it and see if there are any. So the code space of a stabilizer code is the joint +1 eigenspace of the stabilizer group. And in the surface code, when you're introduced to it from a condensed matter perspective, you may have seen a Hamiltonian wave first, and then that Hamiltonian is a ground state space. Well, that ground state space is the same as the code space, because if you look at the ground states, they all satisfy the +1 condition of the stabilizers of the toric code or the surface code. Errors in a stabilizer code are just some Pauli strings, some particular Pauli strings that take you out, or maybe don't, and cause an uncorrectable error. Here, the errors that you see, they're framed as little excitations, little local excitations in your surface code. And these local excitations, they create pairs of so-called anions, and they're just nothing but errors. Okay, for the surface code, I don't put abelian topological order here because things get a lot messier. You can talk to Tyler and Nat about these things. There's some of the experts in the audience about that, but only for surface code is this really kind of all the errors are anions and all the anions are air. The small ones, at least, local ones. QEC conditions, we discussed this already. So there's these general conditions for some set of noise operators. So in a surface code, you have induced some sort of geometry on your qubit space. And what you want is to correct few body, so local, geometrically local, and even more generally, preferably few body excitations on your code. And here you know that that's true because you know that it's a topological phase, so there's local indistinguishability, and that's just a manifestation of the QEC conditions. The X and Z stabilizer +1 conditions for each individual X and Z stabilizer generator. You can interpret in a physicsy gauge theory way by thinking of Z as some flux through a plaquette, some Z2 flux through a plaquette, right? And the X-type stabilizers as some gauge condition that you're enforcing dynamically, meaning you're enforcing it in the Hamiltonian. You don't have intrinsic gauge symmetry, you have to enforce it. You know, I'm not an expert in this either, but you can also think of this as some symmetry. That's this more general one-form symmetry. That's not a symmetry that acts globally on the space, but it acts on some pieces of it. Maybe you can, Ethan or somebody can correct me if I'm not saying something right. Your logical Paulis, we didn't really go into this, but for the surface code on, say, let's put it on the torus, right? You have these things that go around the non-trivial cycles in the torus. Those are called that in the topological community, at least for the surface code, and those are just called logical gates. And then this last part we're going to get into in the third lecture some more. Turns out this is a very fresh result that are by people I'm not citing here, but there's indeed a connection between condensing different sets of anions and switching stabilizer codes. And I'll define what code switching is later on. Okay? Does this help sort of make some connections that you hadn't done before, or? Yeah. Yeah. So, there's this, you can see when you start cooking up these checkerboards that there's a boundary that has like the white as the outer and the dark as the outer. And if you connect the white and the dark with a Pauli string, I believe that gives you a logical operator. So it's yeah. Yeah, whenever they taught you topology, topological order, and they said, well, the degeneracy depends on the topology. Well, but if you put it in a plane, you can still get different degeneracy. So that's not the whole story. Okay. There's like a defect. Correct. But first they tell you that it's, oh, there shouldn't be anything dependent on the finite details, the microscopic details of the surface. But then they're like, well, but actually there's two types of boundaries. Oh, well, okay. Aren't those microscopic? No, those aren't microscopic details. Those are general they must be topological because the ground state degeneracy depends on them. So there's some sleight of hand with jargon when you learn about planar versus toric. Yeah. Yep. Correct. 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 Geometric locality. So you have some qubits you place in some way, and you have a metric that tells you which qubits are close, which qubits are far. You're indirectly doing that when you put qubits on a square lattice, because your square lattice is telling you by eye, this qubit is far away, this qubit is close. You have a metric space on which your qubits live. You have a notion of distance. The distance has to be such that it's some Euclidean distance in some normal looking embeddable space in 2 or 3 dimensions or whatever. And then you have geometric locality, and with geometric locality, you can show stability of a phase of matter. Now, there's ongoing collaborations with some students here about extending that to non-geometrically local systems and showing stability of phases of matter, et cetera, for non-geometrically local systems. That's when you start going over to the more general case. Okay, so it's all about how the qubits are connected next to each other. It's a nice open problem, extending sort of these notions into, I think it's a very important thing to do. Yeah.
Could I understand the connection between code switching and anion commutation in simple like the core code? I would have thought that if you just condense either E or M anions, polarize all.
We'll get to it. Yeah, I don't want to get to it now. We have to learn some things before that. Okay. Some stabilizer experiments. So these, remember, this is the notation for stabilizer codes. The largest one has been 2425, sort of by the Rydberg people and superconducting circuit people. This one in particular is interesting because they tried to scale it and see how much more gain you can get by increasing the amount of overhead you use. So with stabilizer codes, generally with error correction, the more overhead you have, the more redundancy you have, the better you should be able to do. Well, that's if all of your components are working in the way you expect them to work. And experimentally, it's very important to actually test that you can actually benefit from increasing the overhead of error correction from increasing the error correction overhead. Otherwise, why are you doing it? You shouldn't use error correction at all, and it doesn't work. So these types of experiments are pioneering this sort of sanity check that indeed error correction should be working in the devices that we have at hand. I think the latest paper is actually these guys. Sorry, I don't have the year. Okay, and just one more. I couldn't help mentioning this. I already talked about geometric locality versus non-geometric locality. And so what computer scientists, by the way, call local is actually non-geometrically local, or few body for physicists. Just keep that in mind. And that's what QLDPC codes are. So there, the support of each stabilizer generator is order 1 in the number of qubits, and each qubit talks to order 1 stabilizer generators. Okay, and that does not require any geometric locality. That means you can have some graph and it can still hold. And the graph is not some Euclidean lattice, it's some crazier thing. And that brings you to the study of more general class of codes, which are QLDPC codes. They're few body, but they're not geometrically local. And there's a tension between enforcing geometric locality and getting the absolute best possible performing code. So there is now 3 families of quantum LDPC codes that approach, so these are code families with I going to infinity that approach K being linear in N and D being linear in N. This is as best as you can do. And the problem is that none of these codes are on geometrically local or Euclidean spaces. They're all defined in these highly interconnected things called Cayley complexes, basically. And I do not want to go into that. But it's a lot of expander graphs. It's a lot of this type of theory from classical coding theory that was plugged in here, mixed together with the CSS construction, and out popped these asymptotically good codes. In fact, there are many bounds, some of which Alex is also going to talk about, that show that you not only is geometric locality not required to define these codes, you actually have to drop it. So all your nice phases of matter, when it comes time to actually cook up a code whose density of storage and whose degree of protection is at as best as it possibly can be, you have to drop geometric locality. And these are some of these papers, including Bobby-Koenig theorem, et cetera, that talk about this. So this is a very interesting tension between physics and computer science. And so I think this sort of motivates this idea that you really need to make sure to extend the physics notions of phase of matter and stability to these more exotic non-geometric local systems. Yeah. I think this has something to do with if you put it on some dimension, if you have a stabilizer code on some Euclidean lattice in some dimension, then you get only a gate in the Clifford hierarchy in that level of the Clifford hierarchy that's the same dimension. I think it has something to do relating spatial dimension of the qubits to the sort of smallest gate you can get. But codes that have gates in the Clifford hierarchy don't get you the full Clifford group, because otherwise they'd be universal. No. So you either get the full Clifford group, or you get part of the Clifford group and then some other thing that you can cut up into this thing called the Clifford hierarchy, and how deep you are into the hierarchy depends on the spatial dimension. That's what I remember. Yeah. Okay. And we finally get to some math. So let's go through a little bit of the structure of stabilizer codes and go back to our nice 4-qubit example. So this is just regurgitating the stabilizer group and this code states. And I already mentioned the advantages, and now let's look at the structure that the stabilizer code induces on our space, our physical state space, and also on the set of Paulis. So stabilizer codes partition Pauli strings into 3 different subsets. And these are the 3 different subsets. The 3 different subsets are you're either a stabilizer, you're a detectable layer, or you're a logical Pauli. So you either act trivially within the code space, or you are a detectable error, you map the code space to an error space, or if you don't do either of these 2, well, then you're going to be doing something within the code space. Okay. This is the P sub L, is the pi sub L logical projection. So what happens when you project that Pauli string into the code space for each of these 3 cases? Well, if you are a stabilizer, you get +1 times the projection. If you are a detectable error, you get 0 because you've taken the code out of the code space. And if you project a logical Pauli into the code space, well, you get a logical operation, which I guess I just call O sub L here, because O could be X, Y, or Z, or anything if you have multiple qubits, some logical Pauli. How do these 3 types of Paulis relate to the stabilizer generators? Well, this is literally an element of the stabilizer group, which means it can be constructed as a product of powers of the stabilizer generators. So there exists some binary string P such that each coordinate of it is some power of some generator, and you can express it in this way. How do detectable errors relate to the stabilizer generators? Well, we remember that the stabilizer generators are our syndromes. There are a good enough set of quantum numbers that label the error spaces. And we remember that our detectable errors move you around error spaces, which means they must change the syndrome, the label, or the eigenvalue of the set of stabilizers. This means that there exists some J, some generator J, that the error anti-commutes with, because it takes us from the code space to the error space that's labeled by the -1 eigenvalue of this M sub J. Does that make sense? There could be more than one, but there's at least one if you have a detectable error. We good? Okay. And then logical pallies, the best thing I could come up with here is that, well, they're code preserving, namely they leave you in the code space, but they act non-trivially, which means they're not stabilizers. So they cannot be expressed this way. And they actually, in fact, commute with all the stabilizers. Okay. That's another condition I should put here. M sub J equals M sub J L. They commute with all the stabilizers. They respect the stabilizer structure, and they act as a logical gate in the code. Okay. So first, let's look at detectable errors. So I told you that these are called E. I told you that there exists some stabilizer generator that these anti-commute with. So for example, for the 4-qubit code, this detectable error anti-commutes with this stabilizer. And that means that this detectable error maps you into some error space. Turns out, we can associate our error spaces each with one particular detectable error. There are many detectable errors that take you to the same error space, right? Degeneracy, but we can pick one. And we can let that be sort of the error that is distinguishing that particular code space. And if you look a little deeper into this chart, there's actually even more structure there, just kind of amazing. So, but let's go through this like more carefully. So we have sort of some errors that take us to these error spaces. Here are the error spaces. PQR are the eigenvalues of the stabilizer generators, which are of this. So P is an eigen value of this one. Q is eigenvalue of this one, and R is eigenvalue of this one. And depending on which one of these the errors anti-commute with, that tells you also the eigenvalues. And so you have 8 error spaces and 8 different binary eigenvalues. To sort of make contact with the previous lecture, remember I had some error spaces I labeled with 0z, 1z, 0x, 1x. Well, I have those are 3 of those are here, and then the 4th one is just the code space. And then there's a couple more. And here's what's interesting. So this is probably the last thing. Look at these error spaces carefully. My original definition was that a code is a subspace, and it's distinguished. There it is. And all these are auxiliary error spaces corresponding to the code subspace. Now, but what if we drop that assumption and we stop thinking of the code as some distinguished space that we always need to get back into, and think of the error spaces themselves as perfectly good codes? Can we do that? Well, let's look at these error spaces. If we think of this one as a code space, what is the distance of this code? Does it have the same error detecting properties as our distinguished code space? Yes or no? Yes, it does. Namely, each of these error spaces is itself a stabilizer code with stabilizer group generated by the same old set of stabilizers, just with different signs. Okay, so we can think of any one of these as a code space of a 412 code. Okay. That's interesting potentially because this sort of allows us to think of error correction not as some thing that always wants you to map into some distinguished space, but just something that allows you, maybe we can track. If we can maybe track information as it goes between all these spaces, if we do it fast enough, maybe we don't have to actually do some active mapping. Now, for this code, we can't correct anything. We can only detect things. So we cannot do that for this code. But there are other codes that you can correct errors already for the 9-qubit version of this, right? And maybe there, if we just track our error subspaces, in principle, you could imagine not always having to go back into this code space. Okay, so I want to just plant that seed of thinking of a code not as some static space that you have to always get information back into, and something that you're fighting the environment from who's trying to kick you out of it, and you're trying to put it back in, as something more dynamic, because turns out there are other spaces here that have basically the same error correcting properties as the code. And this sort of is going to be nurtured more in the other lectures because it'll make contact with some dynamical things that you're all maybe familiar with already. So in that context, these are called Pauli frames of the code. So again, I want to reiterate, for the error detecting code, you cannot do any sort of tracking because you can't correct errors, but for other codes, you can. And this type of structure still holds. So yeah, so I've covered detectable errors, E, and then next time I'll cover logical Pauli's, L. So I guess with that, I'll stop. Yeah.
So you said that like for stabilizer code, the checks are the stabilizers like that. I kind of understand that for Pauli errors, but like I also don't understand that for Pauli errors, but for that they are not actually correctable. Is there something I can gain, but using other type of like checks which actually project to the same code space, but maybe because of collapse something can reach the logical error?
You want to change, you want to pick a set of checks and error space decomposition that's commensurate with your noise model. Yeah, yeah. This is something that, you know, I know people think about in the bosonic setting. And in fact, they revealed this is by doing experiments. So they did experiments with these lattice code states, which have, you know, just shifted lattices as the error spaces. Okay, and because your noise model is just linear shifts. And so your error spaces are just shifted lattices. Your code states are lattices, so errors just shifted lattices. But in reality, they have photon loss in the cavity. And that's a discrete error that's kind of like a contraction, uniform contraction in phase space. And so, well, how do you reconcile linear shifts with uniform contraction? Well, you kind of don't. And they cooked up a set of Krauss operators, effective sort of Krauss operators that they're sort of, that they kind of were implementing experimentally that had very little to do with the error structure, the error space structure imposed by linear shifts. It more had to do with error space structure imposed by loss operator and its powers. So, and they gained something. They did a reinforcement learner. So these kind of partly through some good guesses of what it should be, and then partly let the learner figure it out. And they actually got a nice robust set of Krauss operators that actually had to do with like the GKP states with the errors acted on them as being error spaces. But now the errors were not linear shifts, they were losses. Something like that could be true for qubits, yes. I just don't know of a nice qubit example, but I'm pretty sure as you get into many body setting, these types of things might become relevant. Although, look, if you're engineering from the get-go, if you're engineering 4-qubit checks for the surface code, then there's not much, you know, leverage or leeway you're going to have to change that, you know. Yeah, I think there's definitely games you can play, tricks you can do like this. The point is to tailor your code to your noise model. Okay. Yeah. Yep.
Last thing that you mentioned, that detectable errors map code space to error spaces are also distinguishable. Like if you're also distinct, you know, it's going to also be thought of as code spaces. That's probably only true for like this unitary errors. Like if you have
Yeah,
some
yeah,
of
yeah.
these other, then it will be not.
I'm talking about only the structure induced on your state space and on your Pauli string space by a stabilizer code. Only in that limited setting is what I'm saying going to be the case. In other cases, it may or may not be the case.
Wondering, this is more CSS, but do people look at non-CSS stabilizer codes a lot, like the generated that? Just like less of a directed.
The computer science people love their CSS codes because it allows them to easily plug in whatever classical codes they have to satisfy some condition, immediately get good quantum codes out. Now, there's also a theorem that shows that for any NKD stabilizer code, non-CSS, there exists a CSS code with like 4N, 2K, 2D, something like that. So like if you add a little more qubits, you basically get a CSS version of the stabilizer code out. And so, and asymptotically, the parameters don't change that much. So people who care about asymptotics don't care about non-CSS stabilizer codes precisely because of this. However, practically, yeah, it matters, especially for small codes. You can get more nicely, more error correction, like with 5 qubits, you can already do a single qubit error correction for a non-CSS stabilizer code, while the smallest number of qubits you can do that with CSS is 7. Moreover, if you want to realize phases of matter, I'm going to have a slide about this. Non-CSS is going to be the way to go. I don't know if Tyler and Nat are going to be giving posters, but you want to talk to them. They definitely require a Y operator for a lot of their constructions.